So let us discuss about Coriolis acceleration. Okay, so it is one of the very interesting and important concept which is needed for gate. Okay, it's very easy. Okay, and after completing everything, okay, regarding what is meant by Coriolis acceleration, magnitude, direction, how to find it, and different examples, okay, of the mechanism which is related to Coriolis acceleration. After discussing everything, after you understood everything clearly, we will do some problems also related to this. And this is one of the very important topic, as I said already, in acceleration analysis especially. So just be with me patiently, okay. So I have taken an example, okay. Consider that there is a link, okay. This is a link, a vertical link, which is hinged at this point, okay, which is hinged at this point. And similarly, I am taking another link, which is also hinged at this point. And there is one slider, okay, which is placed in that, in that link. And similarly, there was one more slider which is placed. So I have taken two, okay. So this is A, let us take, this is example B. Regarding C and D, we will talk about it a bit later, okay. Now, what I am doing was, in case of A, okay, in case of A, I am just applying, okay, you consider that I am giving input, okay, I am giving input, consider I am giving input, I am giving input only to this slider, okay, so this is a position when time is equal to 0, okay, this is a position when time is equal to 0 at the beginning, okay, at time is equal to 0, both this slider and this slider was at the same position, okay, no issues, as I represented in the horizontal line. Now what I'm doing, I'm giving some velocity, okay, to the slider alone for A, okay, for A, I'm giving some velocity, okay, to the slider alone, velocity of slider. But I'm not making this link to rotate, okay, because there was a hinge here, so if there is a hinge, then obviously means that it can rotate, that hinge means what? It's a turning pair, so it can rotate. But I'm not giving any angular velocity to this, I'm not giving any input to this, so so this link is not rotating. Only this slider is going to slide over. Let us consider after some time t. Okay, after some time t, this slider has slided. Okay, this slider has slided. This is the path. Okay, I'm just showing you the path. This is the path in which the slider has slided and it has reached this point. Okay, the slider has slided and it has reached this point. So what is this motion called as? What is this motion called as? Pure translation. I hope you got the point, right? This is pure translation. Right. Now, what about this? Okay, so A case was under pure translation. Now what I will do, I am not allowing the sliders to slide over. Okay, I am not allowing the slider to slide over. I am making only this link to rotate. Okay, by giving some angular velocity. Okay, let us consider I am giving some angular velocity omega. When time was 0. Okay, when time was 0, my slide, this is the position. Now I given some angular velocity. Okay, I have given some angular velocity. So what is happening? This is getting rotated. Okay, this is getting rotated and it is reaching its new position. Let us take, this is the new position. Okay, this is the new position. Let us consider that is after time t. Okay, after time t, that is the new position it has reached. What will happen to the slider? See, I'm not allowing the slider to move. Okay, I'm not allowing the slider to move. So slider will just get rotated. It will just get rotated. And what's going to be the motion? Just focus on the motion of slider. My slider is just going to get rotated. Okay, it's going to rotate it and it's going to reach here. Okay, that is going to be my new position. I will use another color because it will overlap with that. When you are drawing, you can bring little bit that side also so that it won't confuse you. This will be my new position of the slider. Okay, and this is the path. This is the path of the slider. And initially, when it was undergoing pure translation, this is the path of the slider. Okay. Now, what type of motion here it is happening? See, only this link was rotating, right? It's a pure rotation. Okay. So B was under pure rotation. Okay, clear? Now focus on the things which I'm going to say now. Okay. Now what I'm doing, I'm going to consider a motion where both this is happening. See, what is that called as when both this happens? That is combined motion or general motion. I hope you remember this. We have discussed in detail about this earlier when we are doing velocity analysis. So combined motion is nothing but translation plus rotation. Okay, or general motion, whatever you want to call, whatever way you want to call, a general motion or combined motion. Okay. See, combined motion, I hope that you remember Newton's approach which we discussed in engineering mechanics. What we used to do, first when somebody is undergoing combined motion, I will first consider the translation and then I will consider the rotation, so that I will get the exact motion from initial state to final state. So either I will first consider translation and rotation, or I will consider first rotation then translation. I hope you remember that, right? Now focus here. When combined motion happens, okay, so what I'm going to do, I'm going to combine this and I'm going to get the general motion, okay. So when combined motion happens, it's not only this slider sliding, it is this, this link is also rotating. So the slider is sliding over the link and the link was rotating. It's simply slider is sliding over the rotating link. Okay, how to get the final position? What generally you will feel the final position will be according to that, the Newton's approach we discussed. It's something like a summation of this two, right? I hope you could recollect it. We discussed it in Newton's approach. What we used to do, we will focus on translation first, then we will add rotation so that I will get the final state. Now listen. If it is exactly according to that, then what it would have happened, it will translate, right? For translation, it will simply translate and it will reach this position, okay? And after that, rotation, okay, it will reach this position. That is what our discussion all about, right? That is what our discussion all about. So this translation distance, okay, this translation distance will be equal to this, and this rotation distance will be equal to this. Okay, if you want, I will mark it down. This is A, or I will use another. Okay, let this be P and let this be Q. Okay, so this distance will be P and this distance will be Q. So the expected final state will be something like this. This is the expected state, final state. But Coriolis, okay, is a researcher, scientist. He observed that, or first before coming to this, let me go through that also, then I will come for it, okay. Suppose here what I'm doing, I'm first considering translation, then I'm considering rotation. What if I consider rotation and then I consider translation? Obviously, I need to reach the same point only, but anyways, I will show you, okay. So if I consider rotation first, okay, if I consider it is undergoing the same distance, this distance of rotation, okay. So this is where I will reach, okay, I'm just drawing it approximately. Yeah, this is where it will reach, okay, and then it's undergoing pure translation, and then it's undergoing pure translation. So if it undergoes, I will show that also, okay, and then it will undergo pure translation. So initially pure rotation, it has reached here, okay, the slider has reached here, then pure translation, and it has reached somewhere here, okay, same distance translation, okay. So this should be same distance of rotation. What is that? P, right? If I'm not wrong, sorry, Q, same distance of rotation Q, and this is the same distance of translation, so this will be P, okay. So if it rotates by Q and if it translates by P, this is the position it's going to reach, okay. And this is our expectation, right? Because combined motion means what? Translation plus rotation, so this is what our expectation. But Coriolis, not pronouncing it correctly, found that the final position of the link, okay, when a slider slides over a rotating link, okay, he identified that the final position was not this. He identified it is somewhat away from it, okay, it's somewhat away from it, and he identified this is the final position, okay. So this extra acceleration, okay, which we are having, okay, that we are getting here is called as Coriolis acceleration. And similarly here also the same thing, okay, he identified that there was some extra acceleration and he named that acceleration to be Coriolis acceleration. Okay, so if you know this concept of combined motion, that is translation plus rotation, this will be very simple. Combined motion or general motion is what? Generally, we are combining translation plus rotation. So if I combine it, if I represent with the general motion, it indicates that I can, by Newton's approach, divide and rule policy, something like I can go for translation first, then rotation, so that I will reach the final state. So as per our expectation, this is the final state. But we are getting somewhat extra distance covered, and that distance is due to an extra acceleration, and that acceleration is called as Coriolis acceleration. Same thing there. Here I am doing translation plus rotation. There I am doing rotation plus translation. Still I am getting some extra distance, and that extra distance is covered because of an acceleration called as Coriolis acceleration. Okay. So when a slider, okay, you can write it down. If possible, I will write it down. When a slider slides over a rotating link, there will be one additional acceleration comes into play, comes into action, and that acceleration is called as Coriolis acceleration. Okay, so we'll discuss about the magnitude, direction, how to find it, everything one by one. Okay, so now let us focus on the definition, the direction, the magnitude, and how to decide whether the Coriolis acceleration exists or not. Okay, so let me just read down the definition has been already explained to you. Okay, so when both the sliding velocity and angular velocity are combinedly present, a new acceleration is coming into play and coming into action, and that acceleration is known as Coriolis acceleration. And I'm going to use ACO for Coriolis acceleration. The reason was I already used ACP for representing centripetal acceleration, and also I already used AT for representing tangential, so it is better I will go with ACO for Coriolis. Okay, right. So what about the magnitude? See, both sliding velocity and angular velocity is present. I already defined this, like the magnitude of Coriolis acceleration, when I was discussing the coordinate system, right? I hope you remember in kinematics of particles. So the formula will be 2 times of Vs into omega. Okay, so that is going to give me the magnitude. And now coming to Coriolis acceleration, when it exists, it can exist when there is a slider present. So the first thing which you need to check is whether the slider is present or not. If slider is not there, directly conclude that there is no Coriolis acceleration. Okay, so that is the first condition. So you need to check whether the slider is present or not. So slider must exist for sure. But if slider exists in a fixed link, and again there is no possibility for a Coriolis component, a slider should exist in a rotating link. Okay, when a link is rotating, on that rotating link a slider should exist, then only Coriolis present. Okay, so first condition is to check slider exists or not. Second condition is to check on which link the slider is existing. If the slider is existing on the rotating link, well and good. If it is existing on If it is existing on fixed link, then there is no Coriolis acceleration present. Okay, so that is the 2 points which we need to take care of. And now focusing on the direction. Okay, so which has been not written down here, but I will just write it down. Direction of Coriolis acceleration. Okay, see, when it comes to direction of Coriolis acceleration, so it's very simple. Rotate the sliding velocity vector Vs about its tail end in the direction of angular velocity. I will explain what does it mean. Suppose let us consider this is my slider. Okay, I'm just representing my slider as a point. Let us consider the slider is rotating over a link here, and the slider is moving in this direction. Okay, so this is my velocity vector Vs. Okay, this is my velocity vector Vs. Now, I forgot to mention one point here. By 90 degree, okay. Now read the statement here. Rotate the sliding velocity vector Vs by 90 degree about its tail end. Okay, where is my tail end? If this is my sliding velocity, this is my tail end. Okay, this is my tail end. So about its tail end, by about this point, I need to rotate this velocity vector in the direction of angular velocity. Let us consider the link is there, right? That link was undergoing a rotation with the angular velocity omega in this direction. What is that direction? Clockwise direction. So what I need to do? Simple, rotate the angular velocity in the direction of omega by 90 degree about its tail. So this is my tail and this is angular velocity omega, so rotate it. So rotate it by 90 degree, okay? See, angular velocity omega was in clockwise direction, so I need to rotate this 90 degree in clockwise direction. So this is going to be the vector, right? And this is nothing but our Coriolis acceleration. Simply rotate your velocity, sliding velocity vector in not anti-clockwise, in the direction of angular velocity by 90 degree about its tail end. Okay, so I'm going to discuss many examples, okay, so that you will have a clear idea about it. So I have taken 4 different examples here. Okay, so let me take, this is A, okay, this is B, this is C, and this is D. These are the 4 different cases. I want you guys to pause the video and check whether what are all the cases are correct, which means what are all the cases where I drawn the direction of my Coriolis acceleration, correct direction of Coriolis acceleration, and which of the cases are wrong and how to correct it. What is the correct one? Okay, so pass it, do it, and then you watch it. Anyways, I'm going to explain it. Okay, right. So first, let us take with case A. This is our sliding velocity, and this is my tail. Okay, about its tail, rotate the sliding velocity in angular velocity direction. This is my angular velocity direction in 90 degree. That is, you have to rotate it by 90 degree, right? So angular velocity was clockwise. Okay, it is clockwise. So rotate it clockwise by 90 degrees. So this is going to be my acceleration, Coriolis acceleration. So 90 degree in clockwise. So am I written it correctly? Yes. So this is correct. Now, going for option B, okay, that is going for next example B. Like they might ask you an 1 mark question, MSQ question also even. Okay, they might give this option A, option B, option C, and option D, and they will ask you which of the options are correct. Okay, consider it as an MSQ question. Okay, right. So what about this? This is my VS. Okay, this is my VS. And angular velocity was in this direction, anti-clockwise direction. Okay, it was in anti-clockwise direction. So this is how it's going to be by 90 degree. Of course, I need to rotate it by 90 degree in counterclockwise direction. So this is my Coriolis component. So that Coriolis component which I drawn is wrong. Okay, so option B is wrong. Okay, option A is correct. Now focusing on option C, sliding velocity was acting down. Okay, sliding velocity was acting down. This is my tail. And angular velocity was clockwise. Angular velocity was clockwise. Clockwise. Okay, clockwise. So about the tail only I need to rotate. Okay, this is my tail. So about this tail I need to rotate it by clockwise. Okay, clockwise. Clockwise means what? VS. This is the clockwise direction. This is the clockwise direction. This is my clockwise direction. 90 degree. So yeah. So this will be my ACO again 90 degree in clockwise direction. Why clockwise? Because omega was clockwise. Okay. So the given acceleration was wrong. This will be my correct. Okay. Now final B. So this is VS. Okay. And it was in anti-clockwise direction, right? That is my angular velocity was in anti-clockwise direction. Again about tail. About tail, anti-clockwise means what? This side. Okay. This side. Anti-clockwise means what? This side. Okay. So this will be my Coriolis acceleration. So 90 degree in anti-clockwise. It's counterclockwise. And it is correct. Okay. This is correct. So option A, D is the correct answer. Okay, they can ask you in MSQ question like this. Okay, now let us focus on what is that? The different types of mechanism which we seen. What are the 3 different types of mechanism which we seen? 4 bar. Okay, 4 bar mechanism or 4 bar chain, whatever, and single slider chain or single slider mechanism. Okay, single slider mechanism and double slider mechanism. These are the 3 different mechanism, and we seen all the inversions and all the detailed discussions about everything. Okay, now the thing here was you need to decide out of these 3 mechanism in which mechanism we will be having Coriolis acceleration and which we won't have. See, first condition for Coriolis acceleration is slider must present. In A, obviously slider is not there because it's a 4 bar mechanism. We have only 4 links. So slider is not there. Moving to option B, single slider mechanism. Slider is there. Okay, it is satisfying the first condition, but second condition, we have to check the inversions. Okay, we have different inversions. We have to check all the inversions to find out whether it is satisfying second condition or not. Okay, double slider. Again, it has a slider. But again, second condition, whether it is satisfying the second condition or not. What is the second condition? Slider should present in the rotating link. It should not present in the fixed link. If it is present in the fixed link, we won't have Coriolis component. If it present in a rotating link, we will have. So the second conditions we need to take. We need to check. So here in A, obviously no Coriolis component. So directly ACO will be 0. Okay, acceleration for all the inversions. For all the inversions of 4 bar mechanism, ACO will be 0. But now coming to B and C, we have to check the second condition and decide whether ACO will be 0 or will ACO exist. Okay, so let us check that. So now let's focus on single slider chain and double slider chain and find out what are all its inversion where we will be having Coriolis component. Okay. Now first case is slider crank mechanism. Okay, so here we know that there is a slider. Okay, so we need to check both the conditions of Coriolis acceleration. That's it. First condition was the slider present. Of course, yes, the slider is present. But where does the slider present? That is important. The slider is simply reciprocating on the fixed link. So slider is not present on a rotating link. It's present on the fixed link. So ACO will be 0. Okay, so there is no Coriolis component when it comes to simple slider crank mechanism. That is IC engine, compressors and all those things. Okay, right. I already given you the examples. Fine. Coming to Whitworth quick riddle mechanism. Okay, so we are fixing the shortest link. So we will be having two cranks, right? So this and this both will be, the slotted lever and also the crank, both will be undergoing complete 360-degree rotation. And do I have slider? Of course I have slider. And where is my slider placed? It's placed on both are rotating actually. So it is placed on a rotating link, right? So the second condition is also satisfying. So slider is there and slider is placed on the rotating link. So Coriolis acceleration is not equal to 0. I can simply say that exists. Okay, Coriolis acceleration exists. Now coming to third case, what is that? Crank and slotted lever mechanism. Okay, I'm fixing this link. Okay, link 3. Okay, here link 2, here link 3. So if I fix link 3, what will happen? Again, in crank and slotted lever, one I will be getting it as a rocker and another will be crank 360 degree, right? So slotted lever will be my rocker. Okay, still rocker, what actually rocker is doing? It is rotating only, partial rotating. Of course, it's not undergoing continuous rotation, but partial rotation. So still it is rotating. So first condition, does it contain slider? Yes, it contains slider. Does the slider is placed on the rotating link? Of course, yes. This is my slotted lever, which is a rotating link only. Of course, not continuous rotation, but still rocker is also a rotating link only. So 2 is also satisfied. So Coriolis acceleration exists. Okay. Now, hand pump, slider present. Okay, first condition satisfied. But what about 2? Is my slider placed on a rotating link? See, slider is present, but here slider is fixed. Slider is not going to move. It is a fixed link, right? Since it is a fixed link, the second condition has no validity here. Even though slider present, it's a fixed link. Okay, so there is not going to be any Coriolis acceleration because the slider is not moving at all. Okay, so that's it about single slider chain. Okay, sorry. I'm very sorry. It is second condition is becoming 0, right? Sorry, second condition is not valid, right? So acceleration will become 0. Okay. Now moving forward for double slider chain. So what are the 3 inversions we have? Elliptical trammel, Scotch yoke mechanism and whole ham coupling. Elliptical trammel in the sense I will be fixing the slotted lever, and Scotch yoke I will be fixing the link 2, that is any link 2 or link 4, that is I will be fixing this slider or this slider. Whole ham coupling I will be fixing the link 3, that is the coupler. Okay. Right. Now focusing on elliptical trammel. Do I have slider? Of course, I have 2 sliders. Does the slider placed on rotating link? No. Here it is fixed link. We are simply, for all these 3, I have shown you the animation in the earlier video when I was explaining you the inversion. That time itself, you guys clearly know that elliptical trammel, the sliders will just slide. That's it. They are not going to, the slider is not placed in a rotating link. Okay, simply only sliding, only VS will be there. So 2 is not there. So yes, Coriolis acceleration was 0. Okay, what about Scotch yoke mechanism? In case of Scotch yoke mechanism, I'm fixing any one slider, this slider or this slider. Okay, and what's going to happen? See, slider itself fixed. Okay, fine, not an issue. But we have one more slider, right? We have one more slider. So we have one more slider. Fine. But does the slider placed on a rotating link, what actually will happen to the slotted lever? Where in case of Scotch yoke mechanism, we will get a SHM, right? I hope you remember, right? We will get SHM, which means there will be continuous oscillations. But this will simply oscillate front and back, but it's not undergoing any rotation. Again, I already shown you the animation. If you watch that, you will understand there is no rotation happening for this link, right? So slider is placed on a link, but that link is not undergoing any rotation. So 2 is wrong. The second condition is not satisfied. So ACO will be again 0. Now focusing on that, whole ham coupling. What is happening to whole ham coupling? I'm fixing the coupler and this will also rotate, this will also rotate. I hope you remember it. sliding plus rotation. Go and watch the animation again. I have shown you already. So when it comes to Oldham coupling, there will be sliding and also there will be rotation. Okay, so it's simply the shaft, right? Okay, one slider will be attached to the shaft, another slider will be attached to the shaft. So there will be sliding and also there will be rotation. So both the conditions are satisfying. Okay, so here when it comes to Oldham's coupling, acceleration, that is Coriolis' component of acceleration, exists. Okay, so in double slider, we have only one place where Coriolis exists, that is Oldham. And in single slider, we have two places, that is Whitworth and also crank and slotted lever. You need to remember the examples also, right? That is the oscillating cylinder engine. Okay, the examples of these two, that also you need to remember it.